Well, hello there, AP Chemistry. What is this little thing here? Oh, I lost my little thing here. So let me get back and bring it back. Hope you guys are doing well. Hope the last couple of days have been pretty good for you. I missed being in school, that's for sure. But I do want to talk to you today, which will be Wednesday. I'm recording this actually Tuesday late afternoon, but I'll have it posted for class for tomorrow. And I want to talk to you a little bit about uh, where we're going with this business about percent composition, because percent composition is, you might say, well, big deal. I can figure out if something is, 24% carbon and 2% hydrogen, big deal. Well, it is a big deal because what we do as chemists is we use that in order for us to determine um, the molecular formula of a chemical compound. So I want to introduce a couple of things to you here. I want to introduce the idea that uh, a chemical compound, when you go into a laboratory and you make something brand new, and when I say that, let's now just stick with things that maybe have carbon, hydrogen, oxygen, and perhaps nitrogen. And those would be more of your organic type compounds. And when I say organic chemistry is many carbon containing compounds, but also biologically active compounds, pharmaceuticals, things like that. But in its broadest sense, organic chemistry is the chemistry of carbon and its associated compounds. Uh, anyway, what you do is, let's say you go into a lab and you synthesize some new chemical compound, maybe an artificial sweetener, for example, and you want to know the molecular formula of that chemical compound. Well, what you would do is you would send that chemical to a laboratory that does something called elemental analysis. Normally, your average chemistry lab would just send it out to a lab that specializes in elemental analysis. So they would run it through some sort of a apparatus that might combust this material and say there's so much carbon, there's so much hydrogen, so much oxygen and nitrogen in this compound, and they would give you the percent composition, or you would be able to somehow figure out the percent composition. Now, from that, we figure out something called the empirical formula. Now, the empirical formula is well, it's the smallest whole number ratios in a chemical formula. This definition I have on the board here is it comes from a book that's online actually, Chemistry Libre, another fantastic chemistry source for learning this material. It's totally free once again. You don't need to be spending hundreds of dollars on textbooks in the 21st century. But anyway, I won't get on a soapbox tonight. I will tell you though, and let me read this to you. Um, it says many of the methods, again, this little paragraph comes from a larger discussion, but I'll read it to you anyway, and we'll go ahead and discuss it. It says many of the methods, however, that chemists use in the laboratory to determine composition of compounds do not give the molecular formula. Okay, there's a word right there, molecular formula. That is the formula as you know it. So, for example, if I'm talking about glucose, as it says later, the formula is C6H12O6. So, um, what we would get is the ability to get the lowest whole number ratio of the elements in a compound. That's called the empirical formula. So that word right there, let's see if I can make a highlighter here. This word right here, empirical formula, is one that we need to know. And the empirical formula is the formula that gives the lowest whole number ratios of the elements in a compound. Okay, you're going to want to know that. It can be the same as the molecular formula. It can be the same as the molecular formula, but it's not always the same. For example, if I have glucose, C6H12O6, right here, if I've got glucose, you could see by the subscripts here, C6H12O6, you can see that those are not the smallest whole number ratios. I could divide that through by 6, and I come up with CH2O. Okay? This gives us the smallest whole number ratios. So if I go ahead and look at that, CH2O, take a look at this. This is kind of interesting. C6H12O6 is glucose. It's a simple sugar. It's a monosaccharide. And if I look at CH2O, the empirical formula for this, I have a carbon, and H2O is water. So the word carbohydrate is actually derived from that. But if I go ahead and I multiply each subscript by 6, I would get back to my original formula, C6H12O6. Okay, so you're saying right now, whoa, I got two different formulas representing the same thing. Well, yes and no. I mean, two entirely different chemical compounds can have the same empirical formula. So you need to have some additional information in order for you to determine the molecular formula. The most important thing you need to do is you need to look at the molecular formula, or excuse me, you need to look at the molar mass of the compound, and that molar mass right there we use to go ahead and calculate the empirical formula to the molecular formula. So that's what we're going to be doing today. We're going to be looking at empirical formula and how to get the molecular formula from that. Now, again, when I look at this definition, it looks like we have a lot of different things here. We will get some information about our chemical compound that will enable us to get the empirical formula. That's number one. Number two, from that empirical formula, we will get information about the molar mass of that chemical compound. That's step number two. And from those two bits of information, we get the molecular formula. Now, both of these tests, the elemental analysis for the empirical formula and the molar mass measurements, are usually done by an analytical lab. And it's up to us to go ahead and do the math business. So let's get rid of this. We don't need to see this anymore. And let's take a look at some um, empirical to molecular formulas. So I'm going to pause this, go ahead and switch over to the whiteboard. Okay, let's take a look here. Looks like we've got some stuff going on here. I just had to pull up the PowerPoint, and okay, I think we're all ready to go here. It says here, determining percent composition from molecular or empirical formulas. It's really, really straightforward. If you are able to go ahead and do that percent composition, it's easy. So let's review that a little bit. If I've got a simple compound like NH3, we know I have 1 nitrogen and 3 hydrogens, okay? And the formula mass is 17.03 AMUs. Nothing big there. Again, also don't forget that's the same as grams per mole, so 17.03 grams per mole. So if I go ahead and get the percent nitrogen, well, I know I have 1 nitrogen, so that's 14.01. Again, either use AMUs or grams per mole, doesn't matter. Divide it by 17.03 times 100, and your chemical compound would be 82.27% nitrogen and 17.76% hydrogen. Nice little patriotic amount of hydrogen there. So you know how to do that. No big deal. Now, if you know those percentages, a compound's empirical formula can be determined from the masses of its constituent elements. So in other words, if you send your sample away and you have some results come back, and you can get the masses, the relative masses of the different elements, you can change them to moles. You know how to do that. And then we can go ahead and figure out the empirical formula. It's pretty much a 3-step process, very easy. So let's take a look at this. Let's say I have a compound and I send it away, and it has 2 elements in it. It has carbon and it has hydrogen. Well, And we know that the ratios of these, or rather the amounts of mass of carbon and hydrogen, I have 1.71 grams of carbon and 0.287 grams of hydrogen. Now, those subscripts, when you see a subscript like C6H12O6, those subscripts represent the relative number of atoms in that compound. So in glucose, I'd have 6 carbon atoms, 12 hydrogen atoms, and 6 oxygen atoms. So going ahead, once I have this information about grams, I convert those grams to moles, and I say 1.17 grams times 1 mole of carbon per every 12.01 grams of carbon. That gives me 0.142 moles of carbon. And down here, 0.287 grams of hydrogen times 1 mole of oh, there's a typo there. That should say 1 mole of hydrogen, 1.008 grams of hydrogen. So right here, let me see here. That should say H for hydrogen. So 0.287 grams of hydrogen times 1 mole of hydrogen per 1.008 grams. That gives me the number of moles of hydrogen. Now, here's a little trick. You go down here and you write carbon with a subscript from up there. Hydrogen with that subscript that you found up here. So, this is pretty ugly. We like whole number ratios. So what you do is divide each by the smallest number of moles. So the smaller number of moles of each of these two, 0.142 and 0.284 is 0.142. So you go ahead and you look at that, and you divide this through, you get 1. You divide this through, you get 2. So this then becomes our empirical formula, CH2. Now, we don't know if that CH2 is C2H4, C6H12. We don't know the molecular formula. All we know is that these carbons and hydrogens are combined in a 1:2 ratio. The next thing we will do is learn how to get the molecular formula. Okay, let's practice another one. It says here, a compound is determined to contain 5.31 grams of chlorine and 8.40 grams of oxygen. So you'd go through, once again, go from grams to moles of chlorine, go from grams to moles of oxygen. You'd set up our little, let's get this pen back here. You'd set up our little formula, divide through by the smallest number. In that case, it's 1.150, like they do right here. Okay, sorry about that. And then you get something where you get a fractional number here. It's ClO 3.5. So you're thinking, I must have done something wrong. Well, no. You're going to get sometimes you're going to get something like a 3.5, or maybe a 3.25, or a 2.25. Well, then what you have to do is clear the fraction away. Because remember, 3.5 is 3.5. So 1 to 3.5 is, in whole numbers, 2 to 7. Okay? So if you see something like a 3.5, you'd have to multiply through. And if you multiply through each subscript, remember there's like a 1 there. We don't see it. That would be a 2 and a 7. If, for example, maybe it said 2.25 and 3, then you'd have to multiply through by 4 to clear that, that 0.25. So again, this is the empirical formula. They have to be whole numbers, and this is the smallest whole number ratio between chlorine and oxygen. We don't know if this is the same as the molecular formula. It could be Cl4 O14. All we know is that it's a 2 to 7 ratio. This flowchart, again, I'll refer you to the relevant pages in the online textbook, but this flowchart shows you how to go through and do the whole thing. Mass of A atom divided by the molar mass gives you moles. Mass of X atom divided by the molar mass gives you the moles. divide by the lowest number of moles. That gives you the ratio. And then we convert our ratio to the lowest whole numbers, and that gives you the empirical formula. Nothing to it. So it says a compound's empirical formula can be determined from its percent composition. And we just spent Tuesday looking at percent composition. So if we have percent composition, and we know that something is so much percent carbon, so much percent hydrogen, that way we can go ahead and we can figure out the empirical formula. Because if we pretend that we have a 100-gram sample, if something is 25% by mass, that means out of 100 grams, we would have 25 grams of that stuff. So when you're looking at percent composition and you want to convert it to empirical formula, we always pretend that we have 100 grams of the compound. And then our relative percentages will just be turned into grams. Then we follow the 3 steps. We convert the element masses to moles using molar masses, divide by the smallest number of moles, and if we need to, reduce any fractions or clear any fractions. Just some things to look at here. And again, these little pictures I'm skipping by. When I refer you to the textbook pages online, do take a look at them because it's interesting stuff. So let's take a look at a problem. It says the bacterial fermentation of grain to produce ethanol forms a gas with a percent composition 27.29% carbon and 72.71% oxygen. What is the empirical formula for this gas? Okay, well, we have our percentages here. Let me highlight those. We have our percentages here. The highlighter's not working. That's because I hit the eraser. And you should know how to do that by now. So now, listen, guys, if we pretend that we have 100 grams of this stuff, well, we know that 27.29 grams of it would be carbon and 72.71 grams would be oxygen. So now we just go through and say, okay, 27.29, change that to moles by using the molar mass conversion. 72.71 grams of oxygen, convert that by using the molar mass conversion. Then make these our little subscripts here. Divide through by the smallest number of moles, in this case 2.272. And when you divide through, you get the empirical formula for that gas, carbon dioxide, CO2. In this case, this is a case where the empirical formula and the molecular formula are the same. And we don't know that yet. I'm just giving kind of a heads up. In this case, it's one of those examples where it is the same. But for right now, we just look at that like the empirical formula, and we don't know if it's C2O4, C3O6. We just know that carbon and oxygen are in a 2-to-1 ratio, or 1-to-2 ratio. We need more information to prove that. Okay, and here's how we use that last bit of information to prove things. A compound's molecular formula can be determined if we know its molar mass. And again, that information would have to be given to you. So the molar mass of a chemical compound divided by the empirical formula's mass gives you some integer, n, and that will tell you what to multiply each of the subscripts by in order for you to calculate the actual molecular formula. Let's look. Okay, if I've got this chemical compound, CH2O, and we are told that the actual compound has a molar mass of 180 grams per mole. If we look at the empirical formula mass for this, we just have to add up a carbon, which is 12, 2 hydrogens, which roughly 2, so that's 14 plus 16. That's going to be about 30 grams per mole. And we're told that the actual molar mass of that is 180 grams per mole. We divide 180 by 30 and you get 6. So what you do is you multiply each of your subscripts by 6, and that gives you the molecular formula for the compound. This number here should always be an integer. If you get something like 6.02 or 5.99, we would call that 6. Now, I suggest to you the following thing. When you're doing these calculations, carry your masses out to the hundredths place, okay? If we start rounding too quickly, we can get some answers that are not so good. So we don't want to round too quickly. That's all there is to it, though. And I'm going to post some problems for you to work on. And once again, I will see you tomorrow. I can't wait to get back to the classroom because I miss everybody. Last day of COVID prison for me. Unfortunately, my wife is stuck at home now till the end of the week because she got the pink and the blue stripe on the test. So hope you're all well and talk to you soon.